Hi everyone, welcome to the fourth and final video going through some past exam questions on transition metal, ligand substitution and precipitation reactions. The first question here is actually a bit of a recap going back to some basic bits on transition metals. So it wants us to give a definition of what a transition element is. Okay, so this is one we need to know. Okay, so a transition element forms at least one ion with a partially filled D subshell. And that is a definition that you need to know. And it then says, show that iron fits this definition by use of full electron configurations of iron as the element and in its common oxidation states. Okay, so if we look up iron on its own as the element, so iron on the periodic table is going to go through all its electron configuration, and it's going to be blah, 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 blah. 4s2, 3d, 1, 2, 3, 4, 5, 6 to get to iron. Okay, and it wants the full electron configuration, so we do need to write this all out. So 1s2, 2s2, and so on, and then 4s2, 3d6, we said. Okay, and then in its common oxidation states, well, we should know this, the common oxidation states of iron are Fe2+ and Fe3+. Okay, those are the two common ones. And you can hopefully see why this is now a 4-mark question. So that's where you're going to get your 4 marks from. Fe2+ then is going to lose 2 electrons from this electron configuration. And remember, the 2 electrons that it's going to lose are going to be the 2 4s electrons. Okay, we fill that up before the 3d, but it also empties out before the 3d. Okay, and then Fe3+ is going to lose 1 more electron, so that's also going to lose 1 electron from the 3d as well. And then we can clearly see then that both of these ions do have a partially filled D subshell. 3d6, 3d5. So therefore iron is a transition element. Okay, so that's quite a nice question, I think. Okay, then we get a 6-mark question here, and it says, describe 1 precipitation reaction and 1 ligand substitution reaction of copper in the +2 oxidation state. And again, this should be a nice question that we're looking forward to, because this is stuff we need to learn, and if they're going to give us 6 marks just for stuff that's straight out of the textbook, it shouldn't really have to think about this at all. It should just be, yep, I've learnt this, I've learnt this, I've learnt this. We need to include the reagents, relevant observations, and balanced equations. Okay, so let's do a precipitation reaction first of all. And let's just do exactly what they've asked us for, right? So the precipitation reaction, the reagent that we need to add is sodium hydroxide. The observation that we'd see would be a pale blue precipitate. And what it's going to make is it's going to make that precipitate of copper 2 hydroxide. So now we need to write the equation. So again, if you've seen previous videos, there's various ways you can write this equation. I'm just going to write it here with an ionic equation, just because that's different to what I've done in previous videos, just so you can see. So you could write this just by saying aqueous copper ions would react with the hydroxide ions to make this precipitate of copper hydroxide. You could write it like that. Previously I've written it with the copper hexa aqua complex here, but this is also fine. So that's our precipitation reaction. Let's just check, have we done everything they asked us to do? We've got the reagent, we've got the observations, we've got the balanced equation. Right, now we need to do a ligand substitution reaction. And make it clear which is which as well. You can see I've made this very obvious. This is a precipitation reaction, this is this one. So just make it really clear. You know, there's nothing wrong with, like I say, laying this out. So you go, you've asked me for this, here it is. You've asked me for this, here it is. And you're much more likely to get the marks. Right, we've got options here. There's 2 reactions of copper that we know about. One is reacting with ammonia, and the other one is reacting with HCl. doesn't matter which one we choose here. We can do either. Let's do the HCl one. Okay. So if we react this with HCl, we end up with a yellow solution as the product. And the reaction that happens here, this time we do need to write it as the copper hexa-aqua complex because it's ligand substitution, so we need to show that it had some ligands in the first place. And if you remember here, we're going to substitute 4 chloride ligands. Okay. We don't need to do state symbols here, I don't think. I don't think we would need to do state symbols there either, really, but it helps because it's making the point that this is a precipitate. Doesn't mention state symbols anywhere, so they're not going to mark us down for that. So this is going to substitute 4 chloride ligands, we said. Remember, because this is a 2+ ion, the chloride ions will all be negative, so if there's 4 of them, it's going to make a 2- complex now, and we're going to have the 6 waters that have been substituted. So again, that's a pretty nice question. You know, if I got both of those questions in my exam, I'd be super happy. 10 marks on that page, where we haven't really had to think or puzzle anything out. That's all just stuff straight out the book, really. So make sure you're prepared for that. If you can't do that, you need to get to the point where you can go, yep, this is stuff that I know about. Okay, right. This question then, I think, requires a little bit more thought. This is not straight out of the book. So what it's saying here, platinum is an extremely unreactive transition element, but it does take part in a redox reaction with aqua regia, mixture of concentrated hydrochloric and nitric acids. 2 products of this reaction are hexachloride platinic acid, nitrogen dioxide. Okay, use oxidation states to show that this is a redox reaction. Okay, so let's try and write this equation here then. They want us to write the equation here. We're going to have to be careful here though, because again, this is a redox reaction, so this really needs to be 2 separate half equations. Let's see how we go. Let's try and write this equation though and see where we get to. So it says platinum is reacting with a mixture of hydrochloric and nitric acid, and then 2 products of this reaction are this hexachloride platinic acid and nitrogen dioxide. Okay, so use oxidation states to show that this is a redox reaction, right? So let's go through the oxidation numbers here then. So platinum here on its own is going to be oxidation state 0 if it's just an element. Hydrogen is always +1, isn't it? So chlorine's got to be -1. Hydrogen's going to be +1 here. Oxygen's -2. There's 3 of them, so that's -6. +1 is -5, so the nitrogen's going to have to be +5 there. Here, the hydrogen's going to be +1. It's kind of awkward because we don't know about the chlorine, but we're going to assume here that the chlorine's going to be -1. And, you know, this is going to be chlorine as a ligand, isn't it? Most likely. So let's assume the chlorine's going to be -1 here. That's going to make that -6. +2 makes it -4. So the platinum's going to have to be +4 here. Do just be careful about this. This isn't a rule, right? Chlorine does change its oxidation state. It's not always -1. But here, if we don't assume it's -1, then how do we know what the plus is? We just can't continue with the question. So we're going to have to assume that it's -1 here. And that's by far the most likely thing, right? That the chlorine is just acting as a Cl- ligand. And over here then, the oxygen's going to be -2. So the nitrogen's going to be +4. So what's going on here? So the platinum has been oxidized from 0 to +4, and the nitrogen here has been reduced, hasn't it, from +5 to +4. So let's just write that out. So platinum oxidized from 0 to +4, and nitrogen reduced from +5 to +4. Okay, now it wants us to write this equation out. So we've done the equation here, but this is not right, is it? It's not balanced by any stretch of the imagination. And because this is a redox reaction, we don't want to just try and balance this equation because we're going to mess it up. We need to have this as two half equations. Now that we've worked out what's being oxidized and what's being reduced, we can do those two half equations. We've not really got any space here, so I'm going to do this at the top. So one of these reactions must involve the platinum being oxidized into this hexachloro, whatever it is. That must be reacting with the HCl, right? That's where the hydrogens and the chlorines are coming from. So that must be that. And the other half equation here must be the HNO3 being reduced to make the NO2. So let's look at the oxidation numbers here. Platinum's gone from 0 to +4, so that's been oxidized. So it's lost electrons, and it's lost 4 electrons, hasn't it? So there must be 4 electrons on this side. And then we must have 6. We've got 6 chlorines here, so this is going to have to be times by 6. And then we can balance the extra hydrogens by just putting H+ ions here. I don't want to change it. I could balance this backwards and forwards forevermore, can I? This is never going to balance with that. If it's 2 hydrogens and 6 chlorines, that's never going to balance. So I can just add my 4 H+ ions to that side, and that balances the charges out as well. Okay, and we don't need to add any waters to this one, do we? Because there's no oxygen in it. Okay, whereas this one, the nitrogen's going from +5 to +4. There is only one nitrogen and one nitrogen. We need to make sure that element's balanced, remember? And there is only one, so that's fine. It's being reduced from 5 to 4, so it's gaining, and it's just gaining 1 electron. So we can add that in here. Then we need to balance the oxygens. I've got 3 oxygens here and I've only got 2 there. So I need to add a water molecule on this side. And then I've got 2 hydrogens and I've only got 1 here. So I add an H+ to this side. And that then also balances my charges up. So I've got no charge and no charge. So that's quite nice. Right, now if I then try and combine these two half equations together, I've got 4 electrons here. I've only got 1 here, so this is all going to have to be multiplied by 4. And it's actually just 1 of everything, isn't there? So that's quite nice. I can literally just go and put a 4 everywhere in here. Now I can add these together. Okay, so therefore I'm going to get platinum plus 6 HCl plus 4 HNO3. Oh, and this is nice as well because the H+ ions are going to cancel out as well as the electrons. They're going to cancel, and those are going to cancel. So platinum and this is going to make 4 NO2 and 4 H2O and this H2 PtCl6. Okay. Now, can you see why we've had to do it that way and we couldn't just try and balance this equation? Because in this equation, we haven't got the water. So there was no way we were ever going to be able to balance this equation. We need to do it by this proper method with the two half equations. Okay. Now, we could have been clever about this because it did give us a sneaky little hint in the question if you're looking for it. Because it does say 2 products of this reaction. Right? Not the products are this, 2 products. Which suggests that there's at least 1 other product, right? Otherwise, they would have just said the products, right? It is worth looking out for this. Okay, this is something the exam board does fairly regularly, is have a mystery product that appears out of nowhere, and the mystery product is pretty much always water, as it is in this case. But it's still worth going through the proper method to work out redox reactions. Okay, so that was actually more of a redox question than transition metals, really. Let's look at this last one then. What's it saying here? Ammonium hexachloroplatinate is a complex of platinum, contains a hexachloroplatinate ion. Draw a 3D diagram. Yeah, so this is going back to what I was saying earlier, where we assumed that the chlorine was -1 because it's acting as a ligand, and here it definitely is. If we'd looked ahead, we could have been actually more confident about that. Right, so if it's got 6 chlorines on a platinum, then it's going to have this standard octahedral geometry. Okay, we should hopefully be comfortable drawing this by now. We'll put all these chlorines on. Right, so draw a 3D diagram to show you the shape of it. That's that. It's octahedral, isn't it? That's what it looks like. Show the charge on the ion. Okay. So the chlorines are all going to be -1, aren't they? So that's going to be -6. The platinum, we know from working this out earlier on, the platinum's +4 oxidation state, isn't it? So +4 -6, so it's going to be a 2- charge overall. And the value of the bond angle, if it's an octahedral complex, then the bond angle is 90 degrees. Okay, that's just one we need to have remembered from year 12.